All right, we'll move on to our next major topic in this course, and that's the steel structures. And just like what we did, the reinforced concrete structures, that we had an overview of the properties and stuffs like that, and then we get into the details of the structural members itself. Then that's going to be the same thing that we'll do here in the steel structure. So we'll first have an overview on the advantages and disadvantages and properties of the steel materials, the steel structures, and then later on in the succeeding topics or succeeding weeks, we're going to discuss the analysis of these structural steel members. Now, of course, since typically this takes the subject on steel structure is actually a semester long, but for us here, we're just compressing it. So there will be topics wherein we're not gonna be able to take up. Okay, but we'll just encounter the things that we need in these agricultural structures. Okay, so to start, steel is another material used in building construction. Its fast erection and stronger strength, as well as its ductile behavior as compared to reinforced concrete, makes it a candidate for building material. You'll often see steel construction having a faster, let's say, faster construction time. They'll be able to erect the framings or the frames or the members in a faster time as compared to reinforced concrete. And that's actually can be related to probably reinforced concrete, or concrete requires setting time. It requires forms, so erection of forms and then setting time before you can further move on to the let's say the next next structural members. So here you can actually um, do it faster because you don't need any setting time, and also the strength is higher as compared to concrete. If you recall that reinforced concrete or concrete has only something like 20 megapascals, or let's say 30 megapascals, but for steel it's like 10 times, so you get 250 megapascals and even higher. Now let's talk about the advantages of steel structures. Now, one of the advantages is its uniformity of material. Okay, so let me write it here. Advantages. So you have a uniformity of material and predictability of properties. Okay, so the properties, it's already tabulated in tables, and of course you have to do the actual. If you want to determine the actual property, then you can have it test. Okay, and the other one is dimensional stability and ease of fabrication. Okay, and probably speed of erection. Okay, so um, even though we say that we have this ease of fabrication, now still um, steel structures, they are actually one characteristic of steel structure is the steel connections. So the connections between, um, for example, you have this column and you have your you're going to attach a beam. Then how do you connect this beam to the column? Then that's gonna be by either bolted connections or by welded connections. And of course, later on we'll discuss this in detail later. But that's the characteristic. So I just brought this up because when you say welding, then of course you need skilled laborers to do the job. Okay, so for the disadvantages, steel is actually susceptible to corrosion. So it oxidizes and therefore it corrodes, and once it corrodes, it's actually decreasing in material. So you're actually decreasing the strength. And what else? You have loss of strength at elevated temperatures. So at high temperatures, Okay, so for example, in an event of fire, then this will produce a catastrophic failure because your strength is actually decreasing or is decreased when there's an elevated temperature. So probably something like maybe 50%. So if you study about the, I think that's the creep properties and what else, the strength at elevated temperatures. Okay, so that's around. I'm not sure if it's 50% of the yield strength, or maybe I'm just confusing this with the fatigue strength, which is something like 50%. Anyways, the point here is that it's the strength is decreased. And lastly, we have this steel is not. I mean, although steel is not combustible, but of course, it should be fireproof. Okay, so with regard to this corrosion thing, that's the reason why you need to have some painting or coatings but for this steel material. So you need to provide a something like a protection. Okay, so now let's discuss what is steel actually. Okay, so what is steel? Now, steel is basically an alloy of iron and carbon. So that is an alloy mixture of two metals, that's iron and carbon. Now, depending upon the ratio of this carbon in terms of weight, percentage of carbon in terms of weight, we have this, let's say, at around 0.15%, and we have this limiting value of 1.7%. Okay, percent, let's say percent carbon, I think this is by weight. Now, if you have a carbon percentage, by the way, you can see that the amount of carbon is just less than 2%, or it's just actually 1.7, or that depends upon the reference. Sometimes there are other reference just say 1.6, but let's just say this value 1.7. So you see, it's just a very small amount as compared to the iron. Now, it is very helpful to be able to understand this, because any composition that is less than 0.15%, that's what you call wrought iron, and any composition carbon content greater than 1.7%, that's what you call cast iron, and in between, that's actually what the steel is. Okay, so in this steel region, you can actually have let's say higher carbon contents rating, so that's gonna affect the properties. Now, in terms of the strength, and let's say carbon, so if we have an increasing carbon, we're actually having higher strength. If you have low carbon, you have actually lower strength. So let's say this is our strength, but the problem is if you have higher contents, yes, you're getting stronger, but your ductility is actually decreasing. Ductility is decreasing, but strength is increasing. Okay, so the issue of this is when you say ductility, then you're actually be able to carry the loads, or you're by undergoing deformation before fracture. So that's the definition of ductility. Okay, so you have high strength, but you are less ductile. Okay, so in the course of, I think that's in machine design or materials and processes course, then I think you discuss this in details. Like for example, you have this much carbon, then that's probably medium carbon steel, or if you add some, let's say, allying elements like chromium, then that's going to be stainless steel. But for us here, we'll just, in this course, ABE161, we'll just say steel in terms of this Fe and C, and probably other allying elements to strengthen the properties. Okay, so tensile strength. Let's discuss the properties. So just like in reinforced concrete, where you subject the specimen. Okay, so in a testing machine, this is also true in steel. Okay, so let's say this is your grip. Okay, this is the grip and this is the specimen. Okay, so steel specimen. Let's say this is our testing machine. And there's actually the grip and then the specimen. Okay, so this is something like the zoom out. Okay, so what it does is basically you're actually pulling this specimen apart. So compared to concrete, concrete is tested using or using compression test, whereas this one is tensile test. Now, in some reference, I think that's in one of the textbook in mechanics of materials says that for ductile materials, it's usually the tensile strength is uh, more or less equal to the compressive strength. Now, that's true for ductile materials. Okay, so once it's being pulled apart, then we I mean there's a report generated and something like this stress strain curve. So the stress strain curve is how much deformation it undergoes when you apply or when you increase the loads. So the typical stress strain curve for a steel is something like this. Okay, so there's a linear region, and then after this point it starts to yield, so it's about to deform, or it's about to something like it's not gonna be nonlinear anymore. Okay, so this one is the Fy, or the yield strength, and the maximum here before it fails, this is F sub u, is called the ultimate tensile strength. Okay, so these two properties, so take note of these two properties because we'll always gonna encounter this in our calculations. Okay, so to simplify this, you can actually draw this in something like this. Okay, so in a straight line fashion, so we have this region, elastic range. This is the elastic range, elastic. Okay, so if we convert it here, that's the elastic range, and from this point to this point, I think this point to this point is the equivalent. That's the plastic range. Okay, so plastic range. So later on in our topic on flexural members, then we're actually gonna follow our discussion on this plastic range, something like plastic strength or plastic section modulus. Anyways, now where do we get this Fy and Fu values? So we can obtain that from the tables. I've included that in our lecture handouts. So, for example, a type of steel, meaning that there are other types. So, meaning some types probably are something like this, and probably other types are much higher and something like less ductile. So that depends. Okay, so we have that, for example, A36. So if you look at our lecture handouts, we have A36, and what's our yield strength? Yield strength. That's let's say 250 megapascals, and our Fu is, it says 400 to 550 megapascals. So that's it's given in terms of range. Okay, so another one is the shear strength. So the shear strength, okay, let's just say F in V, that's the shear strength of steel. That's taken around 0.6 Fy. So we relate the shear strength in terms of the yield strength in tension, and that's 60%. Okay, so now let's talk about the varieties of structural steel. We have A36, and we have for example, 992 steel, and we have A325 steel. Okay, so probably these ones are the most common: A36, A992, and A325. This one is common for bolts, and this one's common for typical plates and some shapes. and this one calling for I-beams. Okay, so just a couple of notes here. You would notice that we have this designation. It says A, then 36. Now for A here, it stands for the ASTM specifications or standards. So that's the, I think that's the American specification for plastic and materials, or you can just check that out. But if you recall in your let's say in your materials and processes course or machine design course, you would notice that you have a different designations, like for example AISI 1020. Okay, so that's a different standards. It's just actually just confirm, just following different standards. This one is following the AISI, that's the American, I think this is Iron and Steel, American Iron and Steel Institute, and this one is the ASTM. Okay, so for we can say it this way. I think we can say it like, for example, if you're dealing with construction industry, construction materials, or steels here, then you would probably go for this ASTM. But for, let's say, automotives and let's say mechanical components or something, then probably we can just I can just refer to these standards AISI. This is what will commonly encountered. Okay, so in terms of graph, we have something like this. So we have this A36 and we have this A92, so slightly higher strength. A36, A992, and for the A3 to 5 for bolts, so something like this. Okay, so you notice that lower grades, again, similar to the reinforced concrete, that for lower grades you have lower strength, but you have greater ductility. So ductility, this portion here, this deformation, so that's it. And for A92, you have a higher, something like a higher grades, higher strength. And for A3 to 5, you have much higher strength, but you have less ductility. Alright, so now let's move on to our standard steel shape. Okay, so hot rolled shapes. If you recall in the course of materials and process for ABE, the difference between hot rolled and the cold rolled, there's actual differences in the microstructure of the material, but basically when we say hot rolled, it's being formed under let's say higher temperature, elevated temperature, and cold rolled, it's just a secondary operations. Okay, so hot rolled shapes, that's coming from a steel, let's say steel mill or steel production plant, and it produces a lot of shapes. So we have this something like this, and we have also much thicker, probably thicker sections, and we also have something like this, and smaller ones probably. Okay, what else? And we have also something like C, and we also have L, and also, okay, so we have this shape. Okay, so it looks like an actually they're commonly referred to as I beams because they shape like an I, but a more precise designation would be uh, based on, I think that's based on AISC, and that's going to be AISC, and that's another standard for, I think this is American Institute for Steel Construction. Okay, so this is American Institute for Steel Construction. So that is different from AISI that we earlier mentioned. Okay, so we have this W shape that stands for wide flange. Okay, so basically we have a this is the flange and this is the web. Okay, so let's say web, this is the flange, and we have a parallel thickness here. But compare that to this one. Okay, something like similar, but actually the difference is it's actually tapered at this point. So that's the S shape. Okay, what else? If we have um, a much thicker, let's say web and flanges. This is web and flange. Then that's gonna be HP. That's bearing piles. This one American standard, and this one is smaller shapes or miscellaneous shapes. That's called M shapes. And here we have channels. So channels, also tapered sections, and we also have angles here. Angles, so meaning um, it's the I think that's also something like tapered on this edge. Okay, so we can have angles that has equal leg. Okay, equal leg angles, and that's L shapes. This one is C shapes, L shape. This is also L shape, but this is unequal leg. Okay, so when you say unequal leg, it's because this leg is not equal or does not have the same dimension as this leg here. We can also have D shapes. Okay, so that's our hot rolled shapes. And for our cold formed, okay, so when we say cold form, it doesn't mean that the temperature is freezing point, but rather we're just compared to this elevated temperature of hot rolling. This can be done probably maybe ambient conditions, meaning they're formed under this ambient conditions. And as I've said, this I think cold rolling is, or cold forming is just this uh, after these main operations. Okay, so for cold form we have a rectangular, and we also have a square, something like square tube, and then this one is a rectangular tube. We also have round, and we can also have something like this pipe. Okay, so this one is rectangular, hollow steel section, so that's HSS, that's hollow steel section. And this one is square, HSS, and this one is round, HSS, and then this one is a pipe. Okay, so the difference between this hollow steel section and the pipe is the way um, you specify it. Okay, so specifications for pipe, if I remember it correctly, I think this is based uh, on the inside diameter. No, no, I think this is based on the nominal diameter. Okay, when I say nominal diameter, it's not actually the outside, it's not actually the inside. Although for some schedules of these pipes, this nominal corresponds to the internal. Okay, so let's just say nominal diameter is a way of designating or calling out this material. Whereas for round, I think that's in outside. It's based on the outside. Okay, so we also have other productions like plates and bars. So when I say plates, so that's actually the typical ones. That's actually 4 feet, or let's say 1.2 meters by 2.4 meters. So you can order that, in the hardware, or say bars. Okay, we can also have something like flat bars. Okay, and just refer to our lecture handouts for the details of this. Now let's move on to the built-up shapes. It's also possible to, for example, if you require strength and you don't have the required, I mean, the available steel shapes is not sufficient for the design, then you can also do built-up shapes. Now, for example, we have this an example of build-up shapes. So we have two channels. So these are channels or C shapes, and then you include something like a plate here or a bar or something. Then that's gonna be a built-up shape. Okay, other ones, like for example, you have this, let's say, plates or bars, and then you welded it here, and then same goes with this point. You're welding. So instead of having the standard I shape, or I mean standard W shape, you're actually fabricating this shape. So that's gonna be under this built-up shapes. So other ones, for example, these double angles. Let's say you're welding it somewhere or something. Okay, so this is commonly found in roof trusses wherein you need an increased capacity, but the strength of these individual L member or L steel, L-shaped steel is not enough. Okay, so that's the build-up shapes. Okay, so now let's move on to the uh, property tables or steel tables. Okay, so we have here um, an example of a property steel table. Like for example, we have these W shapes. Then you'll find here the designation. We have W, for example, W 200 by 100. So the first one, that refers to the nominal depth. So we say depth. This is, you can find the notations here. So we say depth. That's the distance from the top face to the bottom face. But if you find it here, you have 229. So this is the actual depth. This one is the nominal depth. Again, if you recall, when you say nominal depth, it's just something like the way you call that material. Okay, so 200 by 100. This 100 is this one, the nominal mass per meter. Okay, so in this table, you can actually find the various parameters or geometric parameters that we need in the calculations. For example, cross-sectional area. So we can just find it here right away. That's in mm squared. And you can also find the thickness of the web. That's T sub W. This is it, thickness of the web. And you can have also the width or thickness of the flange. Okay, so BF, that's the width of the flange. And you can also have thickness of the flange. Now, other details, like for example here, the BF all over 2TF, that's the compact section area. We'll encounter this when we get into the topic of, let's say, I think that's in flexural members or compression members. Okay, so that's it. And we have these elastic properties. That's also common. We have this moment of inertia and the section modulus, and then the radius of gyration. Okay, so just take note of these values. So even though it says 11, 11, 3, 130 for the moment of inertia, that's 10 to the 6. And also the same goes true with the section modulus. It's 967, but it's times 10 to the 3. And then we have this radius of gyration. That's along x and along y. So when you say along x, if you're bending this section along x, so something like this, if this is the x-axis, then you're actually bending it like this. If you're having a bend like this, then that's on the strong axis. But if you're bending here, okay, so let's say this is the y axis, then that's gonna be the y axis or the weak axis. Okay, and what else? We have this plastic modulus, something like this. I think that's just this something like the section modulus, except that we're referring to the plastic range here. So this one is elastic range, this one is plastic range. Okay, so what else? We can also have tables for channels and for angle bars. or equal leg angles. Now for equal leg angles, I just like to point out this. We have example, we have additional z axis here. So meaning that if you're trying to bend this on z axis, then it's gonna be like that. Okay, so you can just run through the details of this, and when we're doing the calculations, then we can actually get or be more familiar with these tables. Okay, so that's all for our lecture in about this introduction to steel structure. In the next lecture, we'll oh, by the way, for the L-shaped structure, L-shaped steel, for example, if we have 203 by 203 by 28.6, so this one refers to the the width of this leg here. So if they have the same, then meaning that they are actually equal leg angles. And this one, that's the thickness. Okay, so that's the thickness of this leg. Okay, and also we have before I forget, we have this limit state topic. So you can just read this through in our lecture handles. But basically, what it means that when we're dealing with, when we're designing or analyzing steel steel members, we're actually going to encounter this limit states, meaning it's something like the limiting value or at which it will fail. So we have to prevent. Okay, when we're designing, we have to size up the members based on this something like a failure. We have to prevent these failures or these limiting state or values. All right, so see you in the next video for our next topic on tension members.